There's an old saying that 2 heads are better than 1.
Well, when it comes to parallel programming, I say 2 threads are better than 1. I'm Barron Stone.
And I'm Olivia Stone. In this course, we'll introduce you to the fundamental concepts for concurrent and parallel programming.
These are the basic mechanisms you need to develop programs that can do multiple things at once, to take advantage of multi-core processors and parallel hardware.
We'll focus on the general concepts and relate them back to everyday activities in the kitchen to make those ideas easier to understand and have some fun.
Then, to help cement those abstract ideas, we'll demonstrate them in action using the C++ programming language. If you're new to concurrent and parallel programming, this is a great place to start. Let's get to it. The purpose of this course is to give beginner and intermediate programmers a basic understanding of how to write concurrent and parallel programs. To get the most out of it, you should have some programming experience, but you don't need to be an expert. The videos of us working in the kitchen will demonstrate the key concepts in general terms, and then in the C++ code examples, I'll explain the unique terminology and nuances that make C++ different than other programming languages.
If you're interested in concurrent and parallel programming in other languages, be on the lookout for different versions of this course. You'll find the same general concept videos, but we'll show you the example code in another programming language.
For the C++ demonstrations throughout this course, we'll be using GCC and the make utility to compile and link our example programs, specifically G++ version 7.4.0 and make 4.2.1. If you plan to use a different compiler, make sure it supports the C++ 17 standard to follow along. We'll be using Cygwin to emulate a Unix-like POSIX-compliant environment on our Windows 10 computer. If you'll be using Cygwin as well to follow along, use the Cygwin setup utility to install the gcc-g++ and make packages, and add the Cygwin bin directory to your Windows system path. Finally, to edit our source files, we'll be using Visual Studio Code, but feel free to use any code editor that you're already comfortable using. We've written each of the code examples as a single CPP source file, which can be found in the corresponding directory of the downloadable exercise files. For most of the videos, we'll provide you with a beginning state, the code at the beginning of the video, as well as an end state after we've made modifications. We've also included a make file with each of the examples, which you can use to compile and link the example code. Though keep in mind, you may need to modify the contents of the make file if your development environment is configured differently. Let's start by looking at what parallel computing means and why it's useful. Why it's worth the extra effort to write parallel code. A computer program is just a list of instructions that tells a computer what to do, like the steps in a recipe that tell me what to do when I'm cooking. Like a computer, I simply follow those instructions to execute the program. So, to execute the program or recipe to make a salad, I'll start by chopping some lettuce and putting it on a plate. Then I'll slice up a cucumber and add it. Next, I'll slice and add a few chunks of tomato. I'll try not to cry while I slice the onion. And finally, I add the dressing. Done. As a single cook working alone in the kitchen, I'm a single processor, executing this program in a sequential manner. The program is broken down into a sequence of discrete instructions that I execute one after another, and I can only execute one instruction at any given moment. There's no overlap between them. This type of serial or sequential programming is how software has traditionally been written, and it's how new programmers are usually taught to code because it's easy to understand, but it has its limitations. The time it takes for a sequential program to run is limited by the speed of the processor and how fast it can execute that series of instructions. I'll slice and chop ingredients as fast as I can, but there's a limit to how quickly I can complete all of those tasks by myself. Each step takes some amount of time, and in total, it takes me about 3 minutes to execute this program and make a salad. That's my personal speed record, and I can't make a salad any faster than that without help.
That's my cue. 2 cooks in the kitchen represent a system with multiple processors. Now we can break down the salad recipe and execute some of those steps in parallel.
While I chop the lettuce,
I'll slice the cucumber.
and when I'm done chopping lettuce, I'll slice the tomatoes.
And I'll chop the onion.
And finally, I'll add some dressing.
Hold on. Now it's ready.
Finally, the dressing.
Working together, we broke the recipe into independent parts that can be executed simultaneously by different processors. While I was slicing cucumbers and onions, Barron was chopping lettuce and tomatoes. That final step of adding dressing was dependent on all of the previous steps being done, so we had to coordinate with each other for that step. By working together in parallel, it only took us 2 minutes to make the salad, which is faster than the 3 minutes it took Barron to do it alone. Adding a second cook in the kitchen doesn't necessarily mean we'll make the salad twice as fast, because having extra cooks in the kitchen adds complexity. We have to spend extra effort to communicate with each other to coordinate our actions.
And there might be times when one of us has to wait for the other cook to finish a certain step before we continue on. Those coordination challenges are part of what make writing parallel programs harder than simple sequential programs. But that extra work can be worth the effort because, when done right, parallel execution increases the overall throughput of a program, enabling us to break down large tasks to accomplish them faster, or to accomplish more tasks in a given amount of time. Some computing problems are so large or complex that it's not practical or even possible to solve them with a single computer. Web search engines that process millions of transactions every second are only possible thanks to parallel computing.
In many industries, the time saved using parallel computing also leads to saving money. The advantages of being able to solve a problem faster often outweighs the cost of investing in parallel computing hardware.
Parallel computing requires parallel hardware, with multiple processors to execute different parts of a program at the same time. But before you dive into writing software, it helps to understand how different types of parallel computers are structured. One of the most widely used systems for classifying multiprocessor architectures is Flynn's taxonomy, which distinguishes 4 classes of computer architecture based on 2 factors: the number of concurrent instruction or control streams, and the number of data streams. The class names are usually written as 4-letter acronyms that indicate whether they have single or multiple instruction streams and data streams. For example, SIMD stands for Single Instruction, Multiple Data. The simplest of these 4 classes is the Single Instruction, Single Data, or SISD architecture, which is a sequential computer with a single processor unit. If I'm an SISD computer, at any given time, I can only execute one series of instructions, such as chopping, and I can only act on one element of data at a time, this caret.
It's simple, like an old computer. The next class in Flynn's taxonomy is Single Instruction Multiple Data, or SIMD, which is a type of parallel computer with multiple processing units. All of its processors execute the same instruction at any given time, but they can each operate on different data element. As an SIMD computer, our 2 processors are both executing the same chopping instruction, but I'm chopping celery as my data while Barron chops a carrot.
And we'll execute those instructions in sync with each other. This type of SIMD architecture is well suited for applications that perform the same handful of operations on a massive set of data elements like image processing. And most modern computers use graphic processing units, or GPUs, with SIMD instructions to do just that. Our third class is the opposite of SIMD. In a multiple instruction single data, or MISD architecture, each processing unit independently executes its own separate series of instructions. However, all of those processors are operating on the same single stream of data. That's like Olivia executing the chopping instruction while I execute a different peeling instruction. But we're both chopping and peeling the same carrot at the same time.
Yeah, we're not doing that.
As you can see, MISD doesn't make much practical sense, so it's not a commonly used architecture.
But our fourth and final architecture is, in a multiple instruction, multiple data, or MIMD computer, every processing unit can be executing a different series of instructions. And at the same time, each of those processors can be operating on a different set of data. Now I can slice celery while Barron peels carrots.
MIMD is the most commonly used architecture in Flynn's taxonomy, and you'll find it in everything from multi-core PCs to network clusters and supercomputers. Now, that broad MIMD category is sometimes further subdivided into two parallel programming models, which also have four-letter names: Single Program Multiple Data, or SPMD, and Multiple Program Multiple Data, MPMD. In the SPMD model, multiple processing units are executing a copy of the same single program simultaneously. However, they can each use different data. That might sound a lot like the SIMD architecture from earlier, but it's different because although each processor is executing the same program, they do not have to be executing the same instruction at the same time. The processors can run asynchronously, and the program usually includes conditional logic that allows different tasks within the program to only execute specific parts of the overall program. If Olivia and I are both following the same recipe or program, I can execute part of it while Olivia's processor handles a different task. This SPMD model is the most common style of parallel programming, and when we show you programming examples later in this course, we'll structure the code as a single program and execute it on a multi-core desktop computer, which is an MIMD architecture.
Now, if each of our processors is executing a different recipe, that represents the multiple program, multiple data, or MPMD model. In this scenario, processors can be executing different independent programs at the same time, while, of course, also be operating on different data. Typically, in this model, one processing node will be selected as the host or manager, which runs one program that farms out data to the other nodes running a second program. Those other nodes do their work and return the results to the manager. MPMD is not as common as SPMD, but it can be useful for some applications that lend themselves to functional decomposition, which we'll cover later on.
In addition to a parallel computer's architecture, which can be categorized using Flynn's taxonomy, another aspect to consider is
memory. It's important to understand how the memory is organized and how the computer accesses data.
Right. You could put 1 billion processors in a computer, but if they can't access memory fast enough to get the instructions and data they need, then you won't gain anything from having all those processors. Computer memory usually operates at a much slower speed than processors do, and when one processor is reading or writing to memory, that often prevents any other processors from accessing that same memory element. There are two main memory architectures that exist for parallel computing: shared memory and distributed memory. In a shared memory system, all processors have access to the same memory as part of a global address space. Although each processor operates independently, if one processor changes a memory location, all of the other processors will see that change. So, if I change something in our shared memory space,
Hey, that potato is 2 potatoes.
Every other processor sees that change too. Now, the term shared memory doesn't necessarily mean all of this data exists on the same physical device. It could be spread across a cluster of systems. The key is that both of our processors see everything that happens in the shared memory space. Shared memory is often classified into one of two categories: uniform memory access and non-uniform memory access, which are based on how the processors are connected to memory and how quickly they can access it. In a uniform memory access, or UMA system, all of the processors have equal access to the memory, meaning they can access it equally fast. There are several types of UMA architectures, but the most common is a symmetric multiprocessing system, or SMP. An SMP system has two or more identical processors which are connected to a single shared memory, often through a system bus. In the case of modern multi-core processors, which you find in everything from desktop computers to cell phones, each of the processing cores are treated as a separate processor. For this course, we'll be focused on parallel programming within the SMP architecture, and the example code we show you will be running on a multi-core desktop computer. Now, in most modern processors, each core has its own cache, which is a small, very fast piece of memory that only it can see, and it uses it to store data that it's frequently working with. However, caches introduce the challenge that if one processor copies a value from the shared main memory and then makes a change to it in its local cache, then that change needs to be updated back in the shared memory before another processor reads the old value, which is no longer current. This issue, called cache coherency, is handled by the hardware in multi-core processors, so we will not go into detail on it for this course, but it's something you should be aware of if you find yourself working with larger, more complex parallel computing systems. The other type of shared memory is a non-uniform memory access, or NUMA system, which is often made by physically connecting multiple SMP systems together. The access is non-uniform because some processors will have quicker access to certain parts of memory than others. It takes longer to access things over the bus. But overall, every processor can still see everything in memory. These shared memory architectures have the advantage of being easier for programming in regards to memory because it's easy to share data between different parts of a parallel program. The downside is that they don't always scale well. Adding more processors to a shared memory system will increase traffic on the shared memory bus. And if you factor in maintaining cache coherency, it becomes a lot of communication that needs to happen between all the parts. In addition to that, shared memory puts responsibility on the programmer to synchronize memory accesses to ensure correct behavior. But we'll look into that later.
Okay, that's enough about shared memory. In a distributed memory system, each processor has its own local memory with its own address space. So the concept of a global address space doesn't exist. All of the processors are connected through some sort of network, which can be as simple as Ethernet. Each processor operates independently, and if it makes changes to its local memory, that change is not automatically reflected in the memory of other processors. If I make a change to the data in my memory, Barron's processor is oblivious to that change. It's up to the programmer to explicitly define how and when data is communicated between the nodes in a distributed system, and that's often a disadvantage.
Communication is always tough.
The advantage of a distributed memory architecture is that it's scalable. When you add more processors to the system, you get more memory too. This structure makes it cost-effective to use commodity, off-the-shelf computers, and networking equipment to build large distributed memory systems. Most supercomputers use some form of distributed memory architecture, or a hybrid of distributed and shared memory.
But for this course, we'll stick with simple shared memory in an SMP architecture. When a computer runs an application, that instance of the program executing is referred to as a process. A process consists of the program's code, its data, and information about its state. Each process is independent and has its own separate address space in memory. A computer can have hundreds of active processes at once, and an operating system's job is to manage all of them.
Now, within every process, there are one or more smaller sub-elements called threads. These are kind of like tiny processes. Each of those threads is an independent path of execution through the program, a different sequence of instructions, and they can only exist as part of a process. Threads are the basic units that the operating system manages, and it allocates time on the processor to actually execute them.
To conceptualize the relationship between a process and its threads, think of Olivia and I cooking together in the kitchen as being two threads executing as part of the same process.
We both work independently, doing our own tasks that contribute to the overall execution of our program. For example, if we are part of a process to make a salad, my thread might handle retrieving vegetables from the pantry and fridge.
And I'll handle chopping them up. If the program requires other tasks, we might create additional threads to handle those too. Hey, Steve.
Hey.
Can you make some salad dressing?
I sure can.
Now our salad making process has 3 active threads. And when one of those threads finishes executing its instructions,
All done.
it'll exit and leave the remaining threads to continue what they're doing.
Threads that belong to the same process share the process's address space, which gives them access to the same resources in memory, including the program's executable code and data. You can think of the kitchen that our 2 threads are working in like the shared address space for our process. We both have direct access to the same cookbooks containing our instructions or code, and the ingredients that we're cooking with represents the data and variables we're manipulating. The ability for both of us to use these resources is certainly convenient, and it enables us to easily work together. But it does create the potential to cause problems if we don't coordinate our actions, as we'll see later in this course.
Sharing resources between separate processes is not as easy as sharing between threads in the same process, because every process exists in its own address space, its own separate kitchen. In this process, our 2 threads are making a salad, but that other process next door is running a different program. Those threads are baking a cake.
Our variables and data are isolated to this address space, this kitchen, so the threads in the other process can't directly access our salad data.
Good. We don't want you healthy salad makers messing with our cake either.
There are ways to communicate and share data between processes, but it requires a bit more work than communicating between threads. You have to use system-provided inter-process communication mechanisms like sockets and pipes, allocating special inter-process shared memory space, or using remote procedure calls, which is beyond the scope of what we'll be discussing in this course.
Now, it's possible to write parallel programs that use multiple processes working together towards a common goal, or using multiple threads within a single process.
So which is better, using multiple threads or multiple processes?
Well, like most things in programming, it depends. It depends on what you're doing and the environment it's running in, because the implementation of threads and processes differs between operating systems and programming languages. If your application is going to be distributed across multiple computers, you'll most likely need separate processes for that. But as a rule of thumb, if you can structure your program to take advantage of multiple threads, stick with using threads rather than multiple processes. Threads are considered lightweight compared to processes, which are more resource intensive. A thread requires less overhead to create and terminate than a process, and it's usually faster for an operating system to switch between executing threads from the same process than to switch between different processes. Now, before we demonstrate a process with multiple threads in action, let's first take a look at the number of processors that are available on this computer, which we'll be using for demonstrations throughout this course. To do that, I'll press Ctrl-Shift-Escape, which opens the Task Manager, and then go to the Performance tab. Down at the bottom, we can see that this computer has 2 cores and 4 logical processors. Those numbers mean that this computer has 2 separate and complete physical processing cores, and each of those cores supports something called hyperthreading, which enables them to each run 2 independent threads at the same time. So the computer treats those 2 physical cores as 4 logical processors. Now, the hyperthreading in those 2 cores does not mean I'll get double the performance out of each of them. Hyperthreading takes advantage of unused parts of the processor, so if one thread is paused or not using a specific resource, then the other thread may be able to use it. Under certain workloads, that can create performance improvements, but it's highly application dependent. The moving blue graph shows the total percentage of CPU utilization for all of those processors. I don't have much running right now, so the usage stays low, down near just a few percent. If I want to see the CPU usage for each of those processors individually, I can get more information by clicking the Open Resource Monitor link and then selecting the CPU tab. The charts on the right show the total CPU usage on top, and if I scroll down, I can see how much each of the individual processors on this computer are being utilized. The table on the left lists all of the current processes running on this computer, with information including each process's unique process ID number, its PID, its current status, the number of threads, and its average CPU usage. Now, to show you a few threads running in a process, we've created this short example program, which you can find in the exercise files Chapter 2, 0202 Begin Directory. This program defines a simple function on line 9 called CPU waster, which can be used to create a new thread that spins in a while loop forever. It prints the process ID on line 10 using the getPID function, which is declared in the UNI std header, and then on line 11, it uses the getID function to print the current thread ID. After that, the CPU waster enters into an infinite while loop. It's not doing anything useful, but the thread will stay alive forever and continuously use CPU cycles. Down in this program's main function, lines 16 and 17 print messages with the process ID and main thread's ID value. Then after that, the program instantiates two new threads. To create threads throughout this course, we'll be using the C++ standard library's thread class, which is defined in the thread header file. How threads are actually compiled and implemented under the hood can vary between operating systems, but by writing our code using the standard library classes, it should be portable to different development environments. The two new thread objects created on lines 18 and 19, named thread 1 and thread 2, are assigned the CPU waster as their top-level function to execute. After those two threads start, the main thread enters into its own infinite while loop on line 21 to keep the process alive. Now I'll switch over to a command prompt, opened to a folder with the example code, and I'll use the make command to build the program. It warns me that the data type used to represent a thread ID may not be compatible with the printf function because it's not actually an integer data type. But for the sake of this demonstration, that's okay. The printf function will do its best to display the thread ID as a numeric value, which will be enough to at least see that the three threads in this program are different. Now I'll run the executable, thread processdemo.exe. I can see that the operating system assigned this program the process ID number 232, and the main thread has an ID value represented by this number, 98368. The two CPU waster threads that were created have the same process ID as the main thread, but they each have their own unique thread IDs. Switching over to the task manager, I can see that the overall CPU usage has jumped to over 50%. That's because the two CPU waster threads I created are running continuously and using CPU resources on half of the 4 logical processors on this computer. Looking at the Resource Monitor's CPU tab, I can see how that workload is being distributed across all of those processors. If I scroll down in the Processes window, I see a process called thread processdemo.exe. Now, you may have noticed that it has a different process ID number than our program displayed earlier, and that's because we're using Cygwin to emulate a POSIX-compatible environment on our Windows computer. The process ID shown here in the Windows Resource Monitor is the ID that Windows assigned the process. Whereas the value the program printed out was the process ID it got from the Cygwin emulation environment. This program will continue running forever if I don't stop it, so I'll manually terminate it by closing the command prompt window that was running the program. If I look at the CPU usage now, I can see that when I close the program, those CPU wasting threads were terminated too, and the CPU usage dropped back down to just a few %. Just because a program is structured to have multiple threads or processes does not mean they'll necessarily execute in parallel. A concept that's closely related to parallel execution, but often gets confused with it, is concurrency. Concurrency refers to the ability of an algorithm or program to be broken into different parts that can be executed out of order or partially out of order without affecting the end result. Concurrency is about how a program is structured and the composition of independently executing processes. Consider this recipe to make a salad, which includes several steps that involve slicing and chopping vegetables. We can decompose those steps into a collection of concurrent tasks because the relative order in which we do them doesn't matter. They're order independent. To keep things simple, let's just focus on 2 of those tasks for now. I'll chop onions.
And I'll slice cucumbers. This knife represents our computer's processor. We only have one knife, so this is a single-core processor, and only one of us will be able to execute our vegetable chopping routine at any given time.
We'll have to take turns. You go first.
Thanks. My thread will use the processor to execute and slice some cucumbers. Then, after a bit, we'll swap places.
Now my thread gets some time to execute and slice onions.
I want to slice now.
So, we'll swap places again, and we'll keep on doing this until we're both done. In this scenario, we're running concurrently because our 2 independent processes overlap in time. However, since we only have a single processor, only one of us will actually be executing at any instant in time. If we swap places and take turns more frequently, it might create the illusion that we're executing simultaneously on our single processor, but this is not true parallel execution.
To actually execute in parallel, we need parallel hardware. In our kitchen, that means another knife and cutting board, a second processor. But in regards to computers, parallel hardware can come in a variety of forms. Most modern processors used in things like desktop computers and cell phones have multiple processing cores. Graphics processing units, or GPUs, contain hundreds or even thousands of specialized cores working in parallel to make amazing graphics that you see on the screen. And computer clusters distribute their processing across multiple systems. Since we've structured ourselves as concurrent operations, I can begin slicing cucumbers with this processor.
Well, I cut onions with the other one. Now we're actually executing in parallel because we're both executing at the same time, and as a result, we're able to finish the job faster. Concurrency is about the structure of a program, being able to deal with multiple things at once, whereas parallelism is about simultaneous execution, actually doing multiple things at once. Those things could be related, like chopping vegetables, but they don't have to be. Concurrency enables a program to execute in parallel, given the necessary hardware, but a concurrent program is not inherently parallel.
And programs may not always benefit from parallel execution. For example, the software drivers that handle I/O devices, like a mouse, keyboard, and hard drive, need to execute concurrently. They're managed by the operating system as independent things that get executed as needed. In a multi-core system, the execution of those drivers might get split amongst the available processors. However, since I/O operations occur rather infrequently relative to the speed at which computer operates, we don't really gain anything from parallel execution. Those sparse independent tasks could run just fine on a single processor, and we wouldn't feel a difference. Concurrent programming is useful for I/O-dependent tasks like graphical user interfaces. When the user clicks a button to execute an operation that might take a while, to avoid locking up the user interface until it's completed, we can run the operation in a separate concurrent thread. This leaves the thread that's running the UI free to accept new inputs.
That sort of I/O-dependent task is a good use case for concurrency. Parallel processing really becomes useful for computationally intensive tasks, such as calculating the result of multiplying 2 matrices together. When large math operations can be divided into independent subparts, executing those parts in parallel on separate processors can really speed things up. Threads don't just execute whenever they want to. A computer might have hundreds of processes with thousands of threads that all want their turn to run on just a handful of processors. So how do they decide who goes first?
That's the operating system's job. The OS includes a scheduler that controls when different threads and processes get their turn to execute on the CPU. The scheduler makes it possible for multiple programs to run concurrently on a single processor. When a process is created and ready to run, it gets loaded into memory and placed in the ready queue. Think of these as cooks in the kitchen that are ready to work. The scheduler is like the head chef that tells the other cooks when they get to use the cutting board. It cycles through the ready processes so they get a chance to execute on the processor. If there are multiple processors, then the OS will schedule processes to run on each of them to make the most use of the additional resources. A process will run until it finishes, and then a scheduler will assign another process to execute on that processor. Or a process might get blocked and have to wait for an I/O event, in which case it'll go into a separate I/O waiting queue so another process can run. Or the scheduler might determine that a process has spent its fair share of time on the processor and swap it out for another process from the ready queue. When that occurs, it's called a context switch. The operating system has to save the state or context of the process that was running so it can be resumed later. And it has to load the context of the new process that's about to run. If I'm a process that's executing on this processor to chop cucumbers, when a scheduler decides it's time for a context switch, I'll need to pause what I'm doing and store the state of that task.
And as the new process that just got scheduled, I'll load my state information and then begin executing. Now, context switches are not instantaneous. It takes time to save and restore the registers in memory state, so the scheduler needs a strategy for how frequently it switches between processes. There's a wide variety of algorithms that different operating system schedulers implement. Some of these algorithms are preemptive, which means they may pause or preempt a running low priority task when a higher priority task enters the ready state. In non-preemptive algorithms, once a process enters the running state, it'll be allowed to run for its allotted time. Which algorithm a scheduler chooses to implement will depend on its goals. Some schedulers might try to maximize throughput, or the amount of work they complete in a given time, whereas others might aim to minimize latency, to improve the system's responsiveness. Different operating systems have different purposes, and a desktop OS like Windows will have a different set of goals and use a different type of scheduler than a real-time OS for embedded systems. Now, while it's important to understand the concept of scheduling and that it's taking place, you usually don't need to worry about the nitty-gritty details of how the scheduler works because it's often handled under the hood by the operating system. In fact, you might not have any control over when the parts of your program actually execute.
And that's an important thing to keep in mind. Avoid writing programs expecting that multiple threads or processes will execute in a certain order, or for an equal amount of time, because the operating system may choose to schedule them differently from run to run. To demonstrate how scheduling can impact execution, we've written this C++ program that executes two threads, named Barron and Olivia, that continuously chops vegetables for about 1 second. The vegetable chopper function on line 9 takes in a string argument for a name which can be used to uniquely identify this thread. The function begins by initializing a local variable on line 10 to count the number of vegetables this thread chops. The while loop on line 11 will execute as long as the Boolean chopping variable that we initialized on line 7 is true, and with each loop iteration, it increments the value of the local vegetable count variable. Finally, after the while loop finishes, the vegetable chopper function prints out how many total vegetables it chopped on line 14. Down in the main function, on lines 18 and 19, we create two threads to execute the vegetable chopper function and pass in additional arguments, which are the strings Barron and Olivia, which will get passed into the vegetable chopper's name parameter. Now, we're creating and starting these two threads one after the other. So they won't begin at the exact same time, but they'll begin close enough together for the purpose of this demonstration. After starting both threads, the program prints a message and then sleeps for 1 second before setting the chopping variable to false on line 23, which will stop the while loop in both threads. Now I'll switch to a command prompt where I've already used the make command to compile the source file. So I'll run the example, execution scheduling demo.exe. I get an initial message that Barron and Olivia are chopping vegetables. Then after a second, they both finish and print a message with the number of vegetables each thread chopped, which is quite a lot. Even though these two threads started and stopped at roughly the same time, they chopped a very different number of vegetables. It looks like Olivia chopped more than Barron. Scheduling is not always fair. If I run this program again, now Barron and Olivia both end with different amounts than before. As you can see, scheduling is not consistent from run to run, so your programs should not rely on execution scheduling for correctness.
When a new process or program begins running, it will start with just one thread, which is called the main thread because it's the main one that runs when the program begins. That main thread can then start or spawn additional threads to help out, referred to as its child threads, which are part of the same process but execute independently to do other tasks. Those threads can spawn their own children if needed, and as each of those threads finish executing, they'll notify their parent and terminate, with the main thread usually being the last to finish execution. Over the life cycle of a thread, from creation through execution and finally termination, threads will usually be in one of 4 states. If I'm the main thread in this kitchen and I spawn or create another thread to help me, that child thread will begin in the new state.
Hello!
This thread isn't actually running yet, so it doesn't take any CPU resources.
I don't even know what I'm supposed to be doing.
Part of creating a new thread is assigning it a function, the code it's going to execute. Olivia, I need you to slice these sausages. We're making soup.
I can do that. I'm ready to start.
Right. You can start now. Some programming languages require you to explicitly start a thread after creating it.
Now that I've started, I'm in the runnable state, which means the operating system can schedule me to execute. Through context switches, I'll get swapped out with other threads to run on one of the available processors.
Olivia is running independently now, so my thread is free to continue executing my own tasks when it's my turn to get scheduled on the processor.
Oh man, this sausage is frozen. I need to wait for it to thaw before I can continue. When a thread needs to wait for an event to occur, like an external input or a timer, it goes into a blocked state while it waits. The good thing is that while I'm blocked, I'm not using any CPU resources. The operating system will return me to the runnable state when the sausage is thawed.
And that frees up the processor for other threads to use. Now my thread may eventually reach a point where I need to wait until one of my children threads has finished for me to continue on. Maybe I've finished preparing everything else. I've completed all of my tasks, and I need Olivia to finish slicing the sausage. I can wait for her thread to complete its execution by calling the join method. When I call join, my thread will enter a block state, waiting until Olivia's done.
Ah, the sausage is finally thawed. Now I'll go back to the runnable state and continue executing. Now I've finished executing, so I'll notify my parent thread that I'm done. Hey Barron, I'm done! And then I'll enter the final terminated state. A thread enters the terminated state when it either completes its execution or is abnormally aborted.
Since Olivia notified me that she's done, I'll return to the runnable state so I can continue preparing soup. Now, different programming languages may use different names for those states and have a few additional ones, but in general, new, runnable, blocked, and terminated are the 4 phases of the life cycle of a thread. To demonstrate the life cycle of a thread from creation to termination, we've created this example program which recreates the interactions between Olivia and me, where I spawn her as a second thread to help slice sausages to make soup. The Chef Olivia function defined on line 7 begins by printing a message that Olivia has started and is waiting for the sausage to thaw. The thread waits for 3 seconds and then prints a second message that Olivia's done cutting sausage before it finishes execution. Below that, the program's main function represents my actions in the kitchen. It starts by printing a message on line 14 that Barron has started and requests Olivia's help, then creates a new Chef Olivia object. In C++, a new thread will begin executing immediately after the associated thread object is instantiated. So Chef Olivia gets started right away, pending the operating system scheduler, of course. After creating Olivia's thread, Barron continues cooking soup, which is represented by sleeping for 1 second on line 18. Since Barron only sleeps for 1 second after starting Olivia, but Olivia sleeps for 3 whole seconds, Barron will be done well before Olivia, but he needs to wait until she is finished to continue on. This is where the join function comes into play, causing Barron to wait until after Olivia has completed everything she needs to do before continuing. So, Barron calls the join function on line 21. Notice that we're calling the join function on the Olivia thread object from within the main Barron thread. That will block Barron's execution there until Olivia terminates, at which point the main Barron thread will be able to continue on to print its final message on line 23 that they're both done. Switching over to the console, when I run this program, I get a series of messages as output. Messages that begin with Barron were printed by the main thread, and messages that begin with Olivia came from the second Chef Olivia thread. After Barron asked for Olivia's help and started her thread, he was scheduled next and printed a message about continuing to cook before entering into his 1 second sleep. Olivia then printed her starting message and then began her sleep for 3 seconds. Barron continued independently cooking soup for his 1 second and then waited for Olivia to join. Olivia finally finished, which allowed Barron to continue, print his last message, and terminate the program. While C++ doesn't give us a view into a thread's state in regard to whether it's blocked or running in the operating system, we can check whether or not a thread is still considered active by using the joinable function, which returns a Boolean indicating whether or not that thread is alive. I'll add a print statement immediately after creating Chef Olivia's thread on line 15 to show whether or not her thread is still active. I'll use the joinable function on the Olivia thread object, and then a conditional statement to print true or false based on that result. Next, I'll copy and paste that line after the main thread is done with its 1 second of sleep, at which point the Olivia thread should still be sleeping. And finally, I'll copy that line one more time after Olivia's thread joins on line 23. Switching over to the console, I'll make and then run the program with those changes. I see that Olivia's thread is active and joinable immediately after she starts. Then later, while Barron continues cooking soup, Olivia is still considered joinable and active, even though her thread is asleep at that time. Finally, after Olivia's thread is done cutting sausage and terminates, she's no longer considered active, and the joinable function returns false. We often create threads to provide some sort of service, or perform a periodic task in support of the main program. A common example of that is garbage collection. A garbage collector is a form of automatic memory management that runs in the background and attempts to reclaim garbage, or memory that's no longer being used by the program. Many languages include garbage collection as a standard part of their runtime environment, but for this demonstration, I'll spawn my own new thread to handle garbage collection.
Man, what a mess.
Olivia is a separate child thread that will execute independently of my main thread. So I can continue doing what I'm doing here, getting my soup ingredients ready.
Well, I try to reclaim some memory, or counter space, by clearing out Barron's garbage.
This setup, with Olivia running as a separate thread to provide that garbage collection service, will work fine until I'm ready to finish executing. Bam! Now my soup's spiced and ready, my main thread is done executing, and I'm ready to exit the program. But I can't...
because I'm still running. Since Barron spawned me as a normal child thread, he won't be able to exit until I've terminated.
And since Olivia's thread is designed to collect garbage in a continuous loop, she'll never exit. I'll be stuck here waiting forever, and this process will never terminate. Threads that are performing background tasks like garbage collection can be detached from the main program by making them what's called a daemon thread. A daemon thread, which you may also hear pronounced as daemon, is a thread that will not prevent the program from exiting if it's still running. By default, new threads are usually spawned as non-daemon or normal threads, and you have to explicitly turn a thread into a daemon or background thread. Olivia, I forgot to tell you this earlier, but you're a daemon thread.
Oh man, you detached me.
When my main thread is finished executing and there aren't any non-daemon threads left running, this process can terminate. And Olivia's daemon thread will terminate with it.
Since I was terminated abruptly with the process, I didn't have a chance to gracefully shut down and stop what I was doing. That's fine in the case of a garbage collection routine, because all of the memory this process was using will get cleared as part of terminating it. But if I was doing some sort of I/O operation like writing to a file, then terminating in the middle of that operation could end up corrupting data. If you detach a thread to make it a background task, make sure it won't have any negative side effects if it prematurely exits. In this program, to demonstrate detaching a thread, we defined a function called kitchen cleaner on line 7, which represents a periodic background task like garbage collection. The kitchen cleaner uses an infinite while loop to continuously print a message that Olivia cleaned the kitchen once every second. Down in the program's main function, I start a new kitchen cleaner thread named Olivia on line 15. Then the thread prints a series of 3 messages that Barron is cooking, followed by a message that Barron is done on line 20, before finally waiting for Olivia's thread to finish and join. If I run the program, I see those messages from Barron and Olivia displayed. But after the main thread reaches the end and prints its final Barron is done message, the program doesn't exit because the kitchen cleaner thread is still going strong, and it will continue to run forever. So I'll terminate it by pressing Control and the break key. Now, to prevent that from happening, I'll detach the thread named Olivia by calling the detach function after creating it on line 15. This will allow the thread to run independently in the background. It also makes the thread non-joinable, so I can delete the join function on line 22. Now, when I make and run the program again, when the main thread is done executing, Olivia's thread is also terminated, so the process can exit.
One of the main challenges of writing concurrent programs is identifying the possible dependencies between threads to make sure they don't interfere with each other and cause problems. Data races are a common problem that can occur when 2 or more threads are concurrently accessing the same location in memory, and at least one of those threads is writing to that location to modify its value. Fortunately, you can protect your program against data races by using synchronization techniques, which we'll show you later, but to eventually use those techniques, you'll first need to know how to recognize the data race. Olivia and I are 2 concurrent threads working together to figure out what we need to buy from the grocery store. I'll take inventory of the pantry, and when I see that we're running low on something, I'll add more of that item to our shared shopping list.
And while Barron does that, I'll look through my recipe book and I'll add ingredients to our shopping list for the meals I want us to cook this week.
Even though we're two separate threads doing different tasks, we run the risk of a data race because we're both accessing and modifying the same shared resource, our shopping list. Now, to the pantry.
Oh, this garlic mashed potato recipe looks delicious. I'll need 5 potatoes for it. I see that our shopping list already has 3 potatoes on it. 3 plus 5 is 8. So I'll erase 3 and write down 8. As you can see, even a simple operation like adding 2 numbers is actually a multiple-step process. First, I had to read the existing value of that item from the shopping list. Then, I modified the value by adding what I needed to it. And finally, I wrote the result back to the shopping list.
It looks like we're running low on garlic in the pantry. I think we should restock it with 2 more cloves. I see that there's currently 1 clove of garlic on the list. 1 plus 2 is,
My garlic mashed potato recipe calls for 5 cloves of garlic. I see there's currently 1 clove of garlic on the list. 1 plus 5 is 6. So I'll update the list to have 6 cloves on it.
Three. 1 plus 2 is 3. We need 3 cloves of garlic.
And now we have a problem. The shopping list started with 1 clove of garlic. Barron wanted to add 2 more, and I needed to add 5 more. 1 plus 2 plus 5 means we should have ended up with 8 cloves of garlic on this list, but somehow we only have 3. I need more garlic for my mashed potatoes.
We just had a data race. As concurrent threads, it's up to the operating system to schedule when we each get to execute. Right after I read the value of 1 from that shared shopping list, my thread got paused.
Then my thread became active and changed the number of garlic from 1 to 6.
And finally, my thread became active again, and at that point, I was operating with old data in my local memory because I thought the existing value of garlic on the shopping list was still 1. So I finished my operation by changing it to 3. In this example, it was the unfortunate timing of when our threads were scheduled that caused the problem. But the unpredictability of when threads get scheduled means sometimes the data race will occur and cause problems, but other times everything might work just fine. And that inconsistency makes data races a real challenge to recognize and debug.
To demonstrate a data race in code, we've created this simple C++ program that uses 2 threads to concurrently increment a shared variable. The variable on line 6 is a counter for the amount of garlic we should buy and gets initialized to 0. Below that, the shopper function defined on line 8 represents a shopper adding garlic to the shopping list. It uses the for loop on line 9 to increment the count variable 10 times. Down in the program's main function, starting on line 14, we start 2 shopper threads called Barron and Olivia, and then use the join method to wait until they're both done. Finally, we print out the value of the garlic count variable on line 19, indicating how much garlic we should buy. Switching over to the command prompt, I've already compiled the program, so I'll run it with dataracedemo.exe. The output tells me that we should buy 20 garlic. That makes sense. We have 2 threads that are each adding 10 garlic to the counter. And if I run this program several more times, there's a reasonably good chance that we'll continue to get the same answer. It's not guaranteed, but with each shopper only incrementing the count variable 10 times, there are not a whole lot of opportunities for the data race to cause a problem. So, to help make trouble, I'm going to modify the for loop on line 9 so each shopper increments the counter 10 million times. Now the expected output should be 20 million garlic. But when I rebuild and then run this program, I get a value that's well below that. It's only around 10 million garlic. And if I run the program again, I get a different output. Even though the simple garlic count ++ operation is only a single line of code, In the background, the computer is actually performing a 3-step read, modify, write process. My 2 concurrent threads end up stepping on each other's toes and unintentionally overwriting each other's changes to produce an incorrect result. When you realize that one of your programs has a data race, grab a cup of coffee, because that could take a while to hunt down and fix. There are tools that exist to help detect data races, but they're specific to different languages and environments and beyond the scope of this course. Some languages also have compiler flags that you can implement to point out sections of code that had the potential to cause a data race. In my opinion, the best defense against data races is a strong offense, preventing them from occurring in the first place. Since a data race only occurs when at least one of the concurrent threads is modifying the value of a memory location, pay close attention to anywhere you see an assignment operation or an operator like the ++ increment that changes a variable's value. If there's a potential that 2 or more threads could access that variable, then you will almost certainly need to use some mechanism to protect it.
Anytime multiple threads are concurrently reading and writing a shared resource, it creates the potential for incorrect behavior, like a data race. But we can defend against that by identifying and protecting critical sections of code. A critical section, or critical region, is part of a program that accesses a shared resource, such as a data structure in memory or an external device, and it may not operate correctly if multiple threads concurrently access it. The critical section needs to be protected so that it only allows one thread or process to execute in it at a time.
Barron and I experienced a data race as we added garlic to our shared shopping list, because incrementing a value is actually a 3-step process. Read the current value, modify it, and then write back the result. Those 3 steps are a critical section, and they need to execute as an uninterrupted action, so we don't accidentally overwrite each other.
I have an idea. Give me your pencil.
Hey, I was using that.
Now there's only one pencil for us to share, and the rule is that only the person holding the pencil can access the shopping list, either to read or write it. That way one of us won't accidentally read a wrong value because the other one is only halfway done updating it. In this arrangement, the pencil is serving as a mechanism called a mutex, short for mutual exclusion, which you'll also hear referred to as a lock. Only one thread or process can have possession of the lock at a time, so it can be used to prevent multiple threads from simultaneously accessing a shared resource, forcing them to take turns. If either of us wants to access the shopping list, we first need to pick up the pencil to acquire the lock on it. We do whatever we need to with the shared notepad, and then when we're done, release the lock by putting down the pencil. The operation to acquire the lock is an atomic operation, which means it's always executed as a single, indivisible action. To the rest of the system, an atomic operation appears to happen instantaneously, even if under the hood, it really takes multiple steps. The key here is that the atomic operation is uninterruptible.
So, if I grab the pencil,
acquiring the mutex is an atomic action that no other thread can interfere with halfway through. Either you have the mutex or you don't. And now that you do have a lock on our pencil, you can safely execute in the critical section.
I say we already have 10 carrots on the list. I'll add 5 more to that.
Oh, and we're going to need some more onions too.
Well, I currently possess the mutex, so you'll have to wait until I'm done. Threads that try to acquire a lock that's currently possessed by another thread can pause and wait till it's available. There, I'm done with the notepad for now, so I'll release the lock.
And I'll acquire the lock so I can add onions to the list.
Don't forget to release the mutex when you're done.
Okay.
Since threads can get blocked and stuck waiting for a thread in the critical section to finish executing, it's important to keep the section of code protected with the mutex as short as possible. If I take the pencil, execute a critical section by adding more lettuce, and then hold on to the pencil while I contemplate what else to buy,
I'm stuck waiting for Olivia to return the pencil so I can use it. And getting kind of annoyed.
Only thinking about what I want to buy doesn't actually require the shared notepad, so the operation doesn't require mutual exclusion. I should have returned the pencil as soon as I was done updating the list. That way, Barron could use it to execute the critical section while I'm busy doing other things. To demonstrate how to manually enforce mutual exclusion with the mutex, we'll modify the example program from earlier with two shoppers that have a data race as they concurrently increment the amount of garlic to buy. Before creating a mutex, I'll need to include the mutex header in this program. Now, I'll create a new mutex, and because Barron and I used the pencil for our mutex, I'll give it the creative name of Pencil. To keep the two shopper threads from modifying the garlic count variable at the same time, I'll call the pencil mutex's lock member function to acquire the lock on it before entering the for loop on line 11. And I'll call its unlock method after the for loop completes to release the hold on it. Switching over to the command prompt, I'll build that program with the make command, and then run it. The first shopper thread to begin executing will take the pencil, increment the garlic count 10 million times, and then unlock the pencil so the other thread can do the same. That prevents the data race, and I get the expected output of 20 million. Now, that solution seemed to work fine here because incrementing the garlic count is a fairly quick operation, and that's all the shopper thread needs to do, 10 million times each. But what if there was a longer I/O operation involved? Perhaps each of these shoppers needs some time to think and ponder the meaning of life every time they add an item to the list. To simulate that, I'll add a print statement before incrementing the garlic count variable that says the current thread is thinking. Then, after that, I'll use the sleep for function to make that thread sleep for half a second. And that will also require me to include the chrono header at the top. Finally, since I put that sleep method in there, I'll also reduce the number of loop iterations on line 13 down to just 5 for each thread, so it doesn't take forever to run. When I make and run the program now, I see a new thinking message appear every half a second, 5 from one thread, and then 5 from the other, so the program takes about 5 seconds in total to finish. Since each thread does its thinking while holding onto the pencil, the other thread is stuck waiting outside of the critical section during that time. The critical section here is way bigger than it needs to be. I only really need to protect line 16, which increments the garlic count. Sleeping and thinking doesn't affect any shared data, so the shoppers don't need to be holding on to the pencil while they do that. So to improve this program, I'll move the pencil's lock and unlock functions so that the shopper locks the mutex immediately before incrementing the garlic count and then unlocks it immediately afterwards. Now, when I make and run the program, it will run twice as fast because the threads aren't holding onto the pencil while they're busy thinking. I see the thinking messages from both threads appear in pairs, and it only takes 2.5 seconds to execute. We've minimized the critical section to only protect the part of this program that truly requires mutual exclusion. Using a lock to protect a shared variable with mutual exclusion works. But if you're only doing simple operations, like incrementing a variable's value, then a simpler solution is to use C++ atomic types, which encapsulate a value and synchronize access to it to prevent a data race. If I scroll down this documentation page, I see a variety of atomic types, including atomic booleans, characters, integers, long values, and so on. Continuing down the page is a list of functions of the atomic object, which implement many of the common operations. To demonstrate using atomic objects, I'm going to modify the previous example code to demonstrate a data race, which has two parallel threads incrementing a count variable 10 million times. I should get an output of 20 million, but since I'm using a regular integer on line 6, and I don't have any locks in place to protect it with mutual exclusion, when I run this program, it has a data race that produces an incorrect result, less than the expected output of 20 million. To use an atomic object, I must first include the atomic header. Next, I'll replace the garlic count variable on line 7 with an atomic unsigned int, and I'll initialize it to a value of 0. Finally, in the printf section on line 20, I'll use the atomic object's load function to read its stored value. Now, when I make and run the program, I get the correct output value of 20 million because each of the increment operations was executed atomically. Keep atomic objects in mind whenever you need to share something simple, like a counter value between concurrent threads.
Olivia and I have been using this pencil as a mutex. Only one person at a time can own or have a lock on it, and only that person can access our shared resource, this notepad.
If I attempt to lock the mutex while another thread has it, my thread will be blocked, and I need to wait until he unlocks it so it becomes available.
And if I attempt to lock the mutex, it doesn't appear to be available, so my thread will just have to wait too.
It's behind your ear. You already locked it.
Oh. Well, my thread can't unlock the mutex while I'm blocked waiting on it, and I'll be waiting on the mutex forever because I'll never be able to unlock it. I'm stuck, and so are you. If a thread tries to lock a mutex that it's already locked, it'll enter into a waiting list for that mutex, which results in something called a deadlock, because no other thread can unlock that mutex.
There may be times when a program needs to lock a mutex multiple times before unlocking it. In that case, you should use a reentrant mutex to prevent this type of problem. A reentrant mutex is a particular type of mutex that can be locked multiple times by the same process or thread. Internally, the reentrant mutex keeps track of how many times it's been locked by the owning thread, and it has to be unlocked an equal number of times before another thread can lock it. If this pencil is a reentrant mutex, when I pick it up, I lock it.
Now Olivia's thread has a hold on the mutex, so she's the only one that can lock or unlock it.
Since the pencil is reentrant, I can lock it again. Now, the pencil has been locked twice by me, which means I'll have to unlock it twice to fully release my hold on it. If your program needs to lock a mutex multiple times, using a reentrant mutex may seem like an easy way to avoid a deadlock. But if you don't unlock the reentrant mutex the same number of times, you can still end up stuck.
I'm waiting. Thanks. Many programmers like using reentrant locks because it can make things easier. You don't need to worry as much about what's already been locked, and they make it easier to retrofit locks into existing code. As an example, say I have a function to increment a shared counter, and it uses a mutex to protect that operation. If later, I create another function that uses the same mutex to protect some other section of code, and that section of code uses the increment counter function. Since those functions are nested, when I execute my function, it'll end up locking the mutex twice before unlocking it. If I was using a regular non-reentrant lock, that would produce a deadlock, but with a reentrant mutex, this works just fine. Now, like many things in the world of programmers, there are some very strong opinions about whether reentrant locks are good or evil. Some opponents of using reentrant locks will argue that the example I just showed you should be refactored to avoid having nested locks by using a third function that increments the counter and only gets called from within a protected section. I'm not going to advocate either way on this debate. There are pros and cons to both sides.
One use case where reentrant locks are really needed is when writing a recursive function. That is, a function that calls itself. If the function makes a recursive call to itself from within a locked section, it will lock the mutex multiple times as it repeats itself, and then unlock the mutex an equal number of times as it returns and unwinds. Since a reentrant mutex can be used recursively like this, you'll often hear it referred to as a recursive mutex or a recursive lock. Different languages use different terms, but these all basically mean the same thing.
To demonstrate using a recursive mutex with C++, we've modified the previous example that we used to demonstrate a data race and mutual exclusion with two shoppers that concurrently increment the number of items to buy. In this version, we're counting the amount of garlic and potatoes to buy with the variables that are initialized on lines 7 and 8. There are two helper functions on lines 11 and 17 called addGarlic and addPotato, which increment the corresponding garlic count or potato count variables. And each of those functions lock and unlock the same mutex named pencil to enforce mutual exclusion around those operations and prevent a data race. The shopper function simply uses a for loop on line 24 to execute those addGarlic and addPotato functions 10,000 times each. Down in the program's main function, we create and start two shopper threads. Then, after they finish running, we print out the amount of garlic and potatoes to buy. Running this program as is indicates we need 20,000 garlic and 20,000 potatoes. That's quite a feast. Now, let's say every time we add a potato, we also want to add additional garlic, because potatoes and garlic go really well together. To do that, we might add a call to the addGarlic function inside of the addPotato function, immediately after incrementing the potato count. By inserting the addGarlic function, we've effectively nested two calls to the lock function. When the addPotato function gets called, it will lock the pencil. Then, when the addPotato function calls addGarlic, the addGarlic function will lock the pencil again. So the pencil ends up being locked twice in a row by those nested functions, before then being unlocked twice as the functions complete. When I make and run this program, it gets stuck waiting when it tries to lock the pencil a second time. The program doesn't have any output, so I can't really tell what's going on. But if I try to wait for it to finish, I'll be waiting here forever. So I'll press Control and the break key to end it. Fortunately, the fix is simple. All I need to do is change the pencil declaration on line 9 from being a regular mutex to a recursive mutex, which can be locked multiple times before being unlocked. Now, when I make and then run the program, I get the output that we should buy 40,000 garlic and 20,000 potatoes. That makes sense because I increment garlic count in both the addGarlic and addPotato functions. When multiple threads each have multiple tasks to perform, making those threads block and wait every time they attempt to acquire a lock that's already taken may not be necessary or efficient. Olivia and I are two threads doing several different tasks. My thread will be taking an inventory of the fridge to see what things we're running low on, and then add those to the shopping list on our shared notepad. I'll go back and forth between those two tasks.
And my thread is searching through the newspaper for grocery coupons and then adding those items to the shared shopping list. Ooh, there are some good deals this week. Now that I've found some items that I want, I'll take the pencil, which is our mutex, to lock access to the shared notepad so I can add them.
I saw we're low on milk, so now I'll go to acquire the pencil, and I see Olivia has it. If I attempt to lock a mutex in a regular blocking fashion, my thread would enter a waiting state at this point, doing nothing until Olivia unlocks it. If I don't have anything else to do, so I can't continue with other things until after I've accessed the shared notepad, that's okay. It's what has to happen. But in this scenario, I do have other useful things to do that don't require the notepad. I can keep searching the fridge for other things we need. So rather than using the standard locking method to acquire the mutex, I'll use what's called try-lock or try-enter, which is a non-blocking version of the lock or acquire method. It returns immediately, and one of two things will happen. If the mutex you're trying to lock is available, it will get locked and the method will return true. Otherwise, if the mutex is already possessed by another thread, the try-lock method will immediately return false. That return value of true or false lets the thread know whether or not it was successful in acquiring the lock. So, if I try to lock the pencil that Olivia currently has, I know immediately that my attempt has failed, so I can go back to searching the fridge.
There, I'm done writing for now, so I'll unlock the pencil and go back to searching for coupons. Since Barron wasn't blocked waiting for this mutex, it's just sitting unlocked, available for anyone to take. Now, Barron likes to explain try-lock with pencils and notepads. I think of it more like being at a house party with a bunch of your friends, your fellow threads. There's one restroom at the house that everyone at the party will need to use at some point, but only one person can use it at a time. When you try to use it and try opening the door, you realize it's locked because someone's already inside. You could stand there and wait until they come out, or you could go back to the party, keep having fun, and try again later. To demonstrate using try-lock in C++, we created this example which simulates two shoppers searching for items they need, and then adding them to a shared notepad. The variable on line 8 represents the number of items on the notepad. Within the shopper function, each thread has a local variable declared on line 12 for the number of items to add to the notepad, how many items they found in a coupon book, or perhaps missing from the fridge. The while loop on line 13 will keep the shoppers searching for items and adding them to the notepad until there are at least 20 items. If the shopper has items to add to the notepad, they'll execute the if clause on line 14, in which they lock the pencil mutex, add all their items to the list, and print a message with how many items they've added. That then resets their items to add count back to 0. The thread sleeps for 300 milliseconds to simulate time writing things down, and then finally unlocks the pencil on line 20. If the shopper did not have anything to add, then they would have executed the else clause on line 21, where they spend 100 milliseconds searching for and finding an item they need, which then increments their own count of items to add. Down in the main function, we create two shoppers named Barron and Olivia, then record the elapsed time from right before starting their threads until they both finish, to see how long it takes them to find at least 20 items. Switching over to the command prompt, I'll run the program. Notice that the two threads are never adding more than one item at a time. Since the lock function blocks execution while waiting for the mutex to be available, these two threads end up taking turns, swapping places between the top and bottom sections of the if-else statement. Now that the program has finished executing, I see that it took them a little under 6.5 seconds. Now, to modify this code to use the try-lock function, I'll delete the regular lock on line 15. Then I'll add a logical AND operator to the if statement on line 14, followed by pencil.trylock. The order of these statements on each side of the operator matters, because C++ evaluates the left side of a logical AND before the right side. It will first check to see if there are items to add. If and only if the left side of the AND is true, will it evaluate the right side and execute the try-lock function. If the mutex is available, then calling try-lock will immediately lock it and return true, and the program will execute the code on lines 15 through 19 to add items to the shared notepad. If the mutex was not available, then the try-lock function will immediately return false, and that thread will execute the else clause on lines 21 to 23 to look for other things to buy. When I make and run the program now, it executes much faster, finishing in a little over 2 seconds, which is less than half the amount of time it took before. Notice that this time, when one of the threads gets its turn in the critical section, it often adds more than one item to the notepad. With the try-lock function in place, as one thread takes its time writing to the notepad, the other thread is able to jump past that section of code to search for other things to buy multiple times. It's been freed up to go accomplish other things.
We use a lock or mutex to protect a critical section of code to defend against data races, which can occur when multiple threads are concurrently accessing the same location in memory, and at least one of those threads is writing to that location. That second part is key because if we have a bunch of threads and none of them are writing, they all just want to read from the same location, that's fine. It's okay to let multiple threads read the same shared value as long as no one else can change it. They'll all safely see the same thing. Danger only exists when you add a thread that's writing to the mix. When we use a basic lock or mutex to protect the shared resource, we limit access so that only one of the threads can use it at a time, regardless of whether that thread is reading or writing or both.
That works, but it's not necessarily the most efficient way to do things, especially when there are lots of threads that only need to read. This is where reader-writer locks can be useful. A reader-writer lock, or shared mutex, can be locked in one of two ways. It can be locked in a shared read mode that allows multiple threads that only need to read simultaneously to lock it. Or it can be locked in an exclusive write mode that limits access to only one thread at a time, allowing that thread to safely write to the shared resource. A read-write lock is useful for protecting a shared resource like our calendar, because Barron and I frequently need to read the calendar throughout the day.
I can never remember what day it is.
But we rarely need to modify it.
Only once a day.
This marker represents our shared mutex. When my thread wants to read the calendar, I'll lock the mutex in the read-only mode by placing my finger on it.
I also want to read the calendar. I can also place my finger on the marker. Now we both have a shared lock on it, so we can both concurrently read it.
When I'm done checking the date, I'll release my lock on the mutex. Now, I think it's time to increment the calendar's date. In other words, I want to modify it. And to do that, I'll need to lock the shared mutex in the exclusive write mode by picking it up.
But I'm still holding onto the lock to read.
A thread trying to acquire the lock in write mode can't do so as long as it's still being held by any other threads in the read mode. So I'll have to wait.
Done.
Now the shared mutex is completely free, so I'll pick it up to place a write lock on it and update the calendar.
Oh, I already forgot what day it is. And I can't read the calendar now because Olivia has an exclusive hold on the lock to write. Since only one thread can have the write lock at a time, all other threads wanting to read or write will have to wait until the lock becomes available again.
Now, recognizing when to use a read-write lock is just as important as knowing how to use it. In certain scenarios, read-write locks can improve a program's performance versus using a standard mutex. But they are more complicated to implement, and they typically use more resources under the hood to keep track of the number of readers.
And there can be language-dependent differences in how they're implemented that affect performance. Do they give preference to readers or writers that are trying to acquire the lock? Deciding which type of mutex to use is a complicated decision. But as a general rule of thumb, it makes sense to use a shared reader-writer lock when you have a lot more threads that will be reading from the shared data than the number of threads that will be writing to it, such as certain types of database applications. If the majority of your threads are writing, then there's not much, if any, advantage to using a read-write lock. The shared mutex class has been part of the standard library since C++ 17. to provide a mutex that can be acquired in a shared mode, in which multiple threads can share ownership of the mutex, as well as an exclusive mode in which only one thread can have a lock on the mutex. To demonstrate using a shared mutex, this example program creates 10 threads to concurrently read what day it is from a shared calendar, while 2 other threads update it. The calendar here is just an array of strings to represent the days of the week on line 8, as well as an integer to indicate which day today is on line 9. We've created a single regular mutex named marker on line 10, which all of the threads will use to enforce mutual exclusion when interacting with the today variable. There are 2 functions on lines 12 and 21 for the threads that will be reading the calendar value and those that will be writing to update it. They both use a for loop to perform their action of either reading or writing 7 times. In the calendar reader's for loop, the thread locks the marker mutex on line 14, prints out a message about what day it sees, sleeps for 100 milliseconds, and then lets go of the marker. We included the delay here to more easily see when each thread is in the critical section when looking at the program's output. In the calendar writer's loop, the thread takes the marker on line 23, changes the calendar to the next day of the week, prints a message about it doing so, sleeps for 100 milliseconds, and then unlocks the marker mutex. Finally, down in the program's main function, we use a pair of for loops to create and start 10 reader threads and 2 writer threads, so there are 5 times as many readers as writers. When I run this program, a single reader or writer message is printed every 100 milliseconds, indicating that the threads are taking turns in the protected section of code. Only one thread can ever be reading or writing at a time. I see that all of the reads that take place between a writer operation see the same day of the week, and that makes sense. Only the writers are changing the date. So let's upgrade this program to use a shared mutex so multiple readers can view the calendar at the same time. The first thing I'll need to do is include the shared mutex header at the top of the program. Next, I'll modify line 11 to change the marker from a regular mutex to a shared mutex. Finally, I'll change the lock and unlock functions in the calendar reader on lines 15 and 18 to be lock shared and unlock shared. These shared version of the lock and unlock function will allow multiple calendar reader threads to possess the marker mutex at the same time, whereas the standard lock functions on lines 24 and 28 will only allow one calendar writer to access the shared variable at a time. Before I build this program, I'll need to modify our makefile to configure it to use the C++ 17 standard. Depending on the development environment and compiler version you're using, you may or may not need to include this flag to make sure the compiler incorporates newer features, like the shared mutex. Now, when I make and then run this program, I see all of the reader threads enter the protected section at the same time to see what day it is. Then the writers take their turns individually holding the marker to update the calendar before the group of reader threads jump back in to look at the calendar together. The result is a program that finishes much quicker than before.
Olivia and I decided to take a snack break to demonstrate some of the problems that can occur when using locks. A classic example that's used to illustrate synchronization issues when multiple threads are competing for multiple locks is the dining philosophers problem. In this scenario, Olivia and I are 2 philosophers, or threads, doing what philosophers do best: thinking and eating. We both need to access a shared resource, this plate of sushi, and each time one of us takes a piece of sushi, we're modifying its value, the number of pieces that are left. The act of taking sushi from the plate is a critical section, so to protect it, we've devised a mutual exclusion process using these 2 chopsticks as mutexes. When I want to take a bite of sushi, I'll first pick up the chopstick closest to me to acquire a lock on it. Then I pick up the farther chopstick. Now I have possession of both locks. I'm in the critical section, so I'll take a piece of sushi and then put down the far chopstick to release my lock on it, and then the close chopstick. And finally, since I'm a philosopher, I'll go back to philosophizing.
Ah, eureka! That was an interesting thought. Well, I'm feeling hungry now, so I'll acquire the chopstick closest to me. And then the one further away, I'll take a piece of sushi, and then release the far chopstick, and then the one closer to me. As dining philosophers, we'll both continue to alternate between eating and thinking, but since we're operating as concurrent threads, neither one of us knows when the other one wants to eat or think, and that can lead to problems. If I get hungry again and pick up the chopstick closest to me,
And I also get hungry and pick up my close chopstick, I see we've come to an impasse. We've both acquired one of the two locks that we need, so we're both stuck waiting on the other thread to release the other lock to make progress. This is one example of a situation called deadlock. Each member of a group is waiting for some other member to take action, and as a result, neither member is able to make progress. Avoiding deadlock is a common challenge in concurrent programs that use mutual exclusion mechanisms to protect critical sections of code. We want our program to be free from deadlock to guarantee liveness, which is a set of properties that require concurrent programs to make progress. Some processes or threads may have to take turns in a critical section, but a well-written program with liveness guarantees that all processes will eventually make progress. But we're clearly not making any progress here, and I'm getting hangry.
eureka! I have another idea.
Oh, do tell, do tell.
Well, our deadlock occurred because we both reached for the chopstick closest to us first. I grabbed this chopstick first, and you grabbed this chopstick first. That set us up for a deadlock. But if we prioritize these locks so that we both try to acquire this chopstick first, then we won't have this problem because we'll both be competing for the same first lock.
Well, let's give that a try. Ah, brilliant. If you acquire the first chopstick and then I try to acquire it, I'll just be stuck here waiting until you finish taking your sushi and release both locks. Then I can grab that chopstick and this one and take my turn in the critical section.
In this example, we had two separate locks protecting a single shared resource. That may not be the most realistic scenario, but it demonstrates the point. Now, imagine something like a banking application with a set of bank accounts where each one has its own mutex. To ensure that only one thread will be withdrawing from or depositing funds to that account at a time. To transfer funds between two accounts, a thread needs to acquire the locks for both the sender and the receiver, since it would be modifying the value of both accounts. If there are multiple threads concurrently making transfers between the accounts, then there's a real chance that they could end up competing for the same locks and run into this sort of deadlock scenario.
To demonstrate a deadlock, we've created this example program that simulates two dining philosophers thinking and eating sushi. The philosopher function on line 9 takes two reference parameters named first chopstick and second chopstick, which indicate the order in which the philosopher will lock the two mutexes. The while loop on line 10 will continue to run as long as the sushi count variable is positive, which represents the amount of sushi left on the shared plate between the philosophers. We initialize the sushi count to 5,000 on line 7, so our two philosophers should both end up very well fed. Within the while loop, the philosopher will pick up and acquire a lock on their first chopstick, followed by their second chopstick, at which point they're in the critical section. If there's still sushi left on the plate, they'll take a piece by decrementing the sushi count variable on line 14, then finally unlock both chopsticks to put them down for someone else to take. Down in the main function, we initialize two mutexes named chopstick A and chopstick B, then start two philosopher threads named Barron and Olivia. Notice that each philosopher has a different first and second chopstick. Barron will acquire chopstick A first, and then B, whereas Olivia acquires chopstick B first, and then A. After both philosophers have eaten all of the sushi, their threads will finish, and the program will print out a final message on line 27. Switching over to the command prompt, when I run this program, it should take less than a second for our philosophers to eat 5,000 pieces of sushi, but I don't get that final output message. Our philosophers are stuck in a deadlock. If I press Ctrl-Shift-Escape to open the Task Manager, and then go to the Performance tab, I see that the CPU is barely being used. Since the threads are stuck waiting on each other, the deadlocked program doesn't use any CPU cycles. Now, my program will be stuck in this state forever, so I'll need to manually terminate it by pressing Ctrl-Break. I could try running the program again and hope the two philosopher threads get scheduled differently this time, are lucky enough to avoid deadlocking, and make it to the end of the sushi plate. But luck is not a good strategy for programming, so let's implement Olivia's solution of prioritizing the locks. We'll say that chopstick A has the highest priority and B is second. Each philosopher should always take their highest priority chopstick first. I see that on line 24, Olivia takes chopstick B as her first chopstick and chopstick A as her second one, so I'll swap those around. Now both threads will acquire the two chopsticks in the same order. If I make and run the program now, it reaches the end and prints the final message that our sushi-filled philosophers are done eating. Now, we designed this example to be as simple as possible by only including a single shared resource, the sushi plate. In practice, this program only really needs one lock to protect it. We intentionally created the potential for deadlock because we nested two locks inside of each other to demonstrate the concept. As your programs grow in complexity to include more critical sections, locks, and parallel threads with intertwined dependencies, it becomes increasingly more difficult to identify and prevent potential deadlocks. The simplest technique to prevent deadlocks is the one we used in this video, which is to ensure that locks are always taken in the same order by every thread. However, lock ordering may not always be feasible. For example, a thread may not know all of the locks it will need to acquire ahead of taking any of them. For our dining philosophers example, another possible solution in C++ is to use a scoped lock. When you create a scoped lock object, it takes ownership of one or more mutexes and holds onto them for the scope in which that object was created. The scoped lock has a built-in deadlock avoidance algorithm when it's used to acquire multiple mutexes at once. Back in our code, I'll return line 24 to its original state, which creates the potential for a deadlock. Then, I'll replace lines 11 and 12, which lock the first and second chopsticks, with the constructor for a new scoped lock. Creating this scoped lock at the beginning of the while loop will acquire both mutexes and hold on to them until the end of that while loop, at which point the scoped lock is destructed and the mutexes are released. They'll be automatically unlocked, so I don't need these two unlock statements. Switching back to the console, I'll make, and then run the program again, and it finishes right away. But this time, it's using the C++ scoped lock mechanism to avoid a deadlock rather than ordering the locks by priority.
Now that we've figured out how to avoid a deadlock between our two philosophers using chopsticks, we can return to our routine of eating and philosophizing. I'm ready for another piece of sushi, so I'll pick up the first chopstick, then the second one, and I think I left the refrigerator open.
Well, that was rude of him. We've entered another form of a deadlock through thread death. If one thread or process acquires a lock and then terminates because of some unexpected reason, it may not automatically release the lock before it disappears. That leaves other tasks like me stuck waiting for a lock that will never be released and getting hungry.
Sorry about that. Let's look at some code.
To demonstrate what happens if a lock gets abandoned, we'll use a modified version of the previous dining philosophers example that we used to demonstrate a deadlock. In this version, we still have two philosophers, eating and thinking, but we've consolidated the two mutexes into a single mutex simply named chopsticks. The philosophers will lock the chopstick mutex on line 11 before taking a bite of sushi, and then unlocking it immediately afterwards on line 15. With only one mutex at play, the risk of deadlock is removed, so if I run this program, the philosophers successfully take turns eating sushi until all of the pieces are gone. Now, if one of the philosopher threads locks the mutex, and then something happens in the critical section, that thread could finish before it gets a chance to release the lock. To simulate that happening, I'll add another if statement that checks to see if there are exactly 10 pieces of sushi left. And if so, the thread will print a message that this philosopher has had enough. And then after that, they'll use a break statement to immediately break out of the while loop before unlocking the chopstick. When I make and run that program, I get the message that one of the philosophers has had enough, but the other philosopher never finishes eating the last few pieces of sushi. That other thread is stuck waiting on a mutex that will never get unlocked, so the program will be stuck here forever. This scenario is not the same as the deadlock we looked at previously in this course, because the two threads are not waiting on each other to release a lock. But it's a related scenario and the impact is the same. The program isn't making any progress. So I'll press Control Break to terminate the process. A good way to avoid this problem with C++ is to use a mutex wrapper class like the scoped lock. I'll replace the lock function on line 11 with the code to create a new scoped lock object, named lock, using the chopsticks mutex. And then delete the unlock function on line 19. The scoped lock will only hold on to its lock of the mutex for the scope in which the scoped lock object was created, which is the while loop iteration. If something happens to make the loop exit prematurely, like the break statement on line 17, the scoped lock will automatically release its lock on the mutex for another thread to take. If I make and run this program using the scoped lock, it's able to run until the end, even after one of the philosopher threads has had more than enough sushi.
It would be nice if Olivia and I took turns acquiring and releasing the pair of chopsticks so we could each take an equal amount of sushi from the shared plate. But that's not guaranteed to happen. The operating system decides when each of our threads gets scheduled to execute, and depending on the timing of that, it can lead to problems. If Olivia puts down the chopsticks to release her lock on the critical section, but my thread doesn't get a chance to acquire them before she takes them again, then I'll be stuck waiting again until she takes another piece. If that happens occasionally, it's probably not a big deal. But if it happens regularly,
Too slow.
then my thread's gonna starve. Starvation occurs when a thread is unable to gain access to a necessary resource, and is therefore unable to make progress. If another greedy thread is frequently holding a lock on the shared resource, then the starved thread won't get a chance to execute.
In a simple scenario like ours, with two equal threads competing for execution time, starvation probably isn't a concern. both of our threads should get plenty of chances to take sushi. However, if our two threads are given different priorities, then that may not be the case. Barron knows I get grumpy when I don't eat.
And I certainly don't want that, so I'll give Olivia's thread a higher priority.
Thanks.
How different thread priorities get treated will depend on the operating system, but generally, higher priority threads will be scheduled to execute more often. And that can leave low priority threads like me feeling hungry. Another thing that can lead to starvation is having too many concurrent threads.
Oh, I forgot to mention I invited some friends over.
Well, with this many competing threads, I may never get any sushi.
To demonstrate thread starvation, we'll modify this version of the Dining Philosopher's example program to add a local variable within the philosopher function to keep track of how many pieces of sushi each philosopher thread gets to eat. We'll increment the philosopher's sushi eaten variable after they take a piece of sushi on line 15. And then at the end, after their while loop finishes, we'll print a message with the number of pieces this philosopher was able to take. There are currently 5,000 pieces of sushi up for grabs on line 7, so I'll switch over to the command prompt, make, and then run this program. And when it finishes, I can see that each philosopher got a different amount of sushi. It's not necessarily fair, but there's plenty of sushi to go around, so both of the philosophers are well fed. Now, let's see what happens if we drastically increase the number of philosophers at the dinner party by modifying the array to hold philosopher threads on line 23 from having only 2 threads to 200 threads. The following for loops on lines 24 and 27 will then create 200 unique philosopher threads before waiting for them all to finish and join. I'll make and then run the program with that change. And as I scroll through the final counts for each thread, I can see that some philosophers got a decent amount of sushi, but a lot of them didn't get any at all. This one philosopher here took over 1,000. All of these threads were created with the same default priority, but because there were so many threads, some never got scheduled to execute. This represents a real problem in programs containing a large number of threads. For example, if instead of feeding sushi to a bunch of hungry philosophers, this program was a web server that created new threads to handle a huge number of incoming requests, some of those requests may never get processed, and that would lead to some impatient and angry users on the other end. There are techniques that can be used to improve or even guarantee fairness among threads, but that type of workload management is very situational dependent and beyond the scope of this course.
Our greed and competition for sushi has led us to a life of deadlocks and starvation. There's only one piece of sushi left, and I can see you're still hungry. You should have it.
Thank you, my dear. But I can see you're still hungry too. And I would feel like a lousy husband if I allowed my wife to go hungry. You should have the last bite.
Oh, but I can't bear to see you hungry. You shall have the final bite.
Well, this is annoying. We've entered into another tricky situation known as a livelock. A livelock looks similar to a deadlock in the sense that 2 threads are blocking each other from making progress, but the difference is that the threads in a livelock are actively trying to resolve the problem. A livelock can occur when 2 or more threads are designed to respond to the actions of each other. Both threads are busy doing something, but the combination of their efforts prevent them from actually making progress and accomplishing anything useful. The program will never reach the end. The ironic thing about livelocks is that they're often caused by algorithms that are intended to detect and recover from deadlock. If one or more process or thread takes action to resolve the deadlock, then those threads can end up being overly polite and stuck in a livelock. To avoid that, ensure that only one process takes action, chosen by priority or some other mechanism, like random selection.
Rock, paper, scissors for it?
1, 2, 3, shoot!
I win!
Now Olivia gets the last piece of sushi, and that resolves our Livelock.
To demonstrate a Livelock scenario, we'll modify our original dining philosophers example. It creates 2 philosopher threads, Barron and Olivia, which each grab a different first and second chopstick, and therefore have the potential to end up in a deadlock. So let's be clever and implement our own deadlock avoidance algorithm. I'll change the lock function on line 12 for the second chopstick from a regular lock to try lock. And then I'll make that call to try lock the condition for an if statement. If the second chopstick was already taken by another thread, trylock will return false. In that case, this philosopher should politely put back their first chopstick by unlocking it so another philosopher can take it. Otherwise, if the current thread successfully locked both chopsticks, it can continue on as normal, taking a piece of sushi and then unlocking both chopsticks. So I'll enclose that within an else clause. Switching over to a command prompt, I'll make, and then run that program, and hooray! It reaches the end right away. By making our philosophers polite, we've successfully avoided a deadlock. Now, let's invite a few more philosophers to this dinner party. I'll copy and paste lines 26 and 27 to create 2 more philosophers. I'll name them Steve and Nikki. And then finally, I'll call the join functions on Steve and Nikki down near the end. We've only invited 2 more philosophers to this party, and there should still be plenty of sushi to go around. I'll make, and then run that program. And now it's stuck. My first instinct would be to diagnose this type of behavior as a deadlock, but if I press Ctrl-Shift-Escape to bring up the Task Manager, and then go to the Performance tab, I see that the CPU is working hard at 100%. This time, our threads that are trying to avoid a deadlock are instead caught in a Livelock. With 4 philosophers grabbing for the chopsticks, by the time a philosopher has locked their first chopstick and goes for the second one, another philosopher already has it. They're constantly picking up and putting down chopsticks, but nobody can get both at the same time to take a piece of sushi. So I'll need to manually terminate this program by pressing Ctrl-Break. To resolve the Livelock, I'll use the thread's yield function, which will reschedule its execution to allow other threads to run. Exactly how yield accomplishes that will vary depending on its implementation and the operating system scheduler. Back in the code, after unsuccessfully trying to acquire the second chopstick and then putting back the first chopstick on line 13, I'll call the yield function on the current thread. This will cause the thread to temporarily wait for a moment before trying to grab the first chopstick again, which should give another philosopher the chance to get both chopsticks at the same time. For the final time in this course, I'll type make, and then run the program. And I see that it's able to successfully reach the end without getting stuck in either a deadlock or a Livelock.
You've reached the end of this course. We hope it's given you a good foundation of the basic concepts and mechanisms that go into writing concurrent and parallel programs.
And an understanding of the challenges and things that can go wrong.
If you want to continue exploring, we encourage you to play around with the exercise files. See how you can expand on them, or even better, break them.
Take some time to let this new knowledge sink in, and keep an eye out for more related courses. This is the first one in a series of concurrent and parallel programming.
Thanks for watching, and
Happy programming.